Recording and okay, so thank you everyone for coming. It is my absolute pleasure to introduce Oliver Mueller, Dr. Oliver Mueller, I should say, um, who's kindly speaking to us from Europe right now. So Oliver grew up in Basel, Switzerland. He did his bachelor and master's degree in physics at the University of Basel, finishing his master's in 2014. He remained there for his PhD in astronomy, and he earned that in 2018 before taking up his current position as SNF postdoctoral fellow at University of Strasbourg in France, where he's currently speaking to us from. So today he's going to be talking about cosmic ballet of dwarf galaxies and how they present a challenge for modern dark matter cosmology. And with that, I'll leave the floor to you, Oliver. Thank you very much for your time.
Yeah, thank you very much for inviting me, and it's a pleasure, even though it's so remotely. Today, I'm going to talk about dwarf galaxies. Before I'm going to talk about the implications for cosmology, let me briefly just introduce dwarf galaxies, the concept of dwarf galaxies, and also a little bit of the standard dark matter cosmology so that we have a common basis. And then I will dive into one of some peculiar topic which persists now since quite some time actually, and has not been fixed as other problems in cosmology and still remains a puzzle. So first, let me introduce dwarf galaxies. Dwarfs, they come in many shapes and sizes. They can look like this, or at least in Hollywood. So in astronomy, these things are called dwarf galaxies. We see they really come in many different shapes and sizes. They can be huge and quite irregular, like the LMC. Do you actually see my mouse?
Yep, we do.
Yep. Okay, perfect. So like the LMC here on the top left, which is quite irregular, or the WLM, and we have galaxies which are rather elliptical, like Fornax or Sculptor. We have dwarf galaxies which have millions of stars in luminosity, and we can go down to only a few hundred stars. So they really span a huge variety. What is not well represented in this plot is the actual sizes. So if we fix for that, we see that dwarf galaxies, they span a huge variety. Dwarf galaxies, they surround bigger galaxies like the Milky Way or the Andromeda galaxy. So this is a hand drawing of my former PhD supervisor, Bruno Bincali. And he draw here M31, so the Andromeda galaxy, and M33, or here a shape of the Milky Way. And you see the dwarf galaxies, they are smaller. They are smaller than the giant galaxies like the Milky Way or Andromeda. But they surround those bigger galaxies. So they are so-called satellite galaxies. Why are we interested in dwarf galaxies? I would say that this is one of the main, or one of the key relations. If we look into the luminosity and the dynamical mass to light ratio. So this dynamical mass to light ratio, this tells you how much mass do we infer in this galaxy divided by how much light do we see. The higher this ratio, the more hidden mass is in there. And what we see is that for the faintest dwarf galaxies down, or to the left here, that the mass to light ratio goes to over 1000. So there's much more matter in these galaxies than what we can observe. And we explain that with dark matter. So there's a lot of dark matter in there. So if we study dwarf galaxies, we are mainly studying dark matter. So in other words, what we see is just the icing on the cake. So really the stars we see, that's only a tiny portion of the dwarf galaxies. So we have our standard model of cosmology. So we think our universe has these three components of 70% of dark energy driving the expansion of the universe, 25% of dark matter, keeping galaxies together, and only roughly 5% is actually baryonic matter, or what we see, what we can observe, what we know from Earth. So really, most of our universe basically sits in the dark. We know these ingredients. We know the initial conditions of the universe from the cosmic microwave background. So if we know the components of the universe, we know the starting point of the universe, we can mash all of this together, put it into some supercomputers, and try to simulate how our universe should look like today. And that's what has been done with several cosmological simulations. One of them is, for example, here the Millennium 2 simulation, a beautiful dark matter simulation where we see only dark matter, so the baryonic content is not in there, but the baryons will follow this distribution. And what we see is that we have some high density areas, so everything which is bright is high density, and everything which is dark is low density. And what we see is this beautiful cosmic web of the universe. So we see vertices, so knots, we see filaments, and we see some regions which are completely devoid of any matter. If we zoom into such a center, for example here, that's where the bigger galaxies reside. So the galaxy clusters, the galaxy groups are really the dense environments. And what we see if we look into the time steps, so really the evolution of these knots, we see that smaller halos, so-called subhalos, they fall in through these filaments into this bigger halos in here, and then they will get accreted. So these filaments, they are the pathways, so they are the highways to drive structure formation. So here we have really a bigger galaxy. It can be an elliptical galaxy of a galaxy cluster or a Milky Way type galaxy, doesn't really matter. But this halo here of this large galaxy will grow from the accretion of the smaller halos here. These smaller halos, those are the dwarf galaxies. So in other words, the accretion, the formation of bigger galaxies in the center, this comes basically from merging of smaller dwarf galaxies. And not all the dwarf galaxies will merge. Some of them will remain and will start to orbit around the big galaxies. So this is simulations. So if we now go to actual observations, let's say our local galactic neighborhoods, the so-called local volume, this is an image of all the galaxies within 10 megaparsec. So the gray band is the Milky Way band, and the dots represent galaxies. But something is wrong here. So I don't know how interactive is a colloquium with its via Zoom. Are there? Yeah.
So are you basically saying that if anyone has questions, just to interrupt? Yeah. Okay.
And also, can I ask a question? What is wrong with this plot here? Does somebody want to make a guess? There's somebody there. There's something odd.
It's not obvious to me.
The anisotropy of the distribution?
There is an anisotropy, yes, but it's not clearly visible because there's something missing. So I hid all the dwarf galaxies. If we add the dwarf galaxies, the picture becomes much more clear. So before I just plotted all the giant galaxies like the Milky Way, and now I added all the smaller galaxies, smaller than the LMC. And now we really see this anisotropy. So we see this filamentary structure. What I want to say here is that if we want to study the structure of the universe, we shouldn't just look at the big giant galaxies. They are easy to spot, and you could see some structure here, but it becomes much more evident if you also add the dwarf galaxies. So to really define structure of the universe, you see by studying the distribution of the dwarf galaxies. And what you see is this filamentary structure here. So this is the local sheet, which we saw in the simulations. And also you see this region, which is completely devoid of any galaxies. That's the so-called local void. We really see exactly what we saw in the simulation. And that's beautiful, because in the simulations, we just put in the initial conditions of the universe, put in gravity, and let it run. And it formed these structures. And now here in the observations, we exactly see this. So this tells us that our lambda CDM model, our dark matter model, works really well to describe the distribution of galaxies in the universe. However, there is a problem, or there is a bunch of problems if you start to really study the details of the dwarf galaxies. For example, there's an incomplete list here in the study of our own local galaxy group, so the Milky Way and Andromeda. For example, there has been this cusp core problem identified, that the dark matter shapes are not as observed as we predict them from the simulation. There's this missing satellite problem that if you just look at the subhalos we see in the simulation, that's of the order of 1,000 around the Milky Way, but we only find something like 50 dwarfs. So there's this mismatch. There's a too big to fail problem. So the size of the dwarf galaxies don't match with what we predict. There's also a funny correlation between the bulge size of galaxies and the number of satellites, which we don't expect. So all these things, they appeared when we compare simulations with observations. Several of them can be solved by adjusting the simulations. For example, introducing stellar feedback. You can destroy subhalos and then get a low number of satellites, so you can mitigate the missing satellite problem. But I just want to talk about one of these problems, and this is the so-called planes of satellite problems, which I did most of work on my PhD and now my postdoc. So that's really where I'm working on. So let's head into this topic, this peculiar topic of planes of satellites. It's actually a super old topic. Already in the almost 30 years ago, Lyndon Bell and Kankles and Demers saw that the dwarf galaxies around the Milky Way, the then known dwarf galaxies, which were something like 6 dwarf galaxies, they saw that they are aligned in some kind of planar structure around the Milky Way. At that time, that was really not of any issue. So Lyndon Bell thought, okay, this could, for example, be of tidal origin, because the LMC, the Large Magellanic Cloud, is part of this. And he thought that, okay, if this galaxy broke up while it was orbiting and falling into the Milky Way, it would break up and have this tidal dwarf galaxies, or this debris along, and so that can naturally form this structure. We were at that time very far away from the lambda CDM model, which we have today. So it was just an observation, but not really an oddity. And what is interesting is that even though that was found with only 6 dwarf galaxies, with the additional detection of dwarf galaxies now in the era of CCD cameras, with SDSS, with the Dark Energy Survey, with all these different surveys, CFHT, we found so many more dwarf galaxies, and the picture still is there. So here is like an edge-on view on this planar structure. So here's the Milky Way, and all those crosses and triangles are the dwarf galaxies. And this really is this plane of satellite. So it really looks like it is, these dwarf galaxies are arranged in a planar structure. There's an additional component which was found first with proper motion with the Hubble Space Telescope data. And this is if we look into the motions. Here now we show it face on. We see that there's some kind of common motion around the Milky Way. So we are now looking at this plane face on, so like this. And what we see is that there is some kind of motion going on here, meaning that there's a motion within this plane of satellites. So most of them are really like co-rotating within this plane. There's this one dwarf galaxy here, which seems to be counter-rotating, and some of them are off, like these two, or this one here and this one here. So not all are participating, but most of the dwarf galaxies seem to co-rotate within this planar structure. Let us quantify that a little bit further and think for a moment if we have some perfectly planar structure like the planets around the sun. So we are really perfectly planar. Then if we look at the orbital poles, which are perpendicular to the orbital plane, then the scatter of these poles, if we just sum up from all these traces here, the poles, that is basically 0. However, if we have a certain thickness towards in this plane, and we now think that, okay, within this planar structure, they try to move as close as possible to this perfectly planar alignment. And we sum up all the different orbital poles. We have some kind of measurement on the alignment with this planar structure. So this scatter here is just the sum of this angular poles. We can now think, okay, what would be the closest just from the geometrical distribution? So we leave the proper motion measurements and the line of sight, so the 3D motions we let out, we just think from geometry. What is the smallest possible spread of these normal vectors? And if we add more and more of these dwarf galaxies, so that's on the x-axis. So if we just take 3 of them, or 4 of them, or 5 of them, or a set of all 11, here this pink line is the closest, the smallest scatter we could expect. The green line is what we actually observe. So these intervals here, those are coming from the uncertainties of the 3D positions, because they are not perfect. So the planar structure is also not perfectly defined. And what we see is that the observed scatter here is actually consistent with the uncertainty bounds. So this really looks like the motion of the dwarf galaxies is within this planar structure, and it seems to be co-rotating. We can have a different look also I try to now convince you to say that there's really some kind of co-rotation. If we think about the evolution of the errors as a function of time, we get better and better data, and this co-rotation is real. So that would mean that the scatter would get smaller and smaller. And because we have HST data, now we have Gaia data, so we got better and better data. So on the left, I show the evolution of the errors as a function of time, which naturally it went down with better observations. And what we see here is, again, the scatter of these orbital poles also went down. So with better and better data, this got closer and closer. This really tells us that there's something going on. So there's some kind of co-rotation going on. But that's not all evidence we have that there's some kind of co-rotation. in the local group. Also, if we look at our neighboring galaxy, the Andromeda galaxy, it looks like there's some kind of common motion. This time not for all the dwarfs, but there's a subsample which also seem to be aligned in this planar structure here. And for these dwarf galaxies, we only have line of sight velocities. But assuming that there's also co-rotation and there's a plane, what we would expect is that on one side they're red-shifted, on the other side they are blue-shifted. So like co-rotation. And this is actually a signal which was found by Rodrigo Ibata and collaborators that 14 out of, how many is it? Yeah, that most of them on the one side are red-shifted and on the other side are blue-shifted. So this is really, again, an indication that there seems to be some kind of co-rotation, but only based on the line of sight velocities, not on the 3D motion as we have in the local group. However, just recently, Tony Son et al. Found with proper motion measurements of two of the brightest satellites so they could measure proper motions with HSD observations, and they found that the proper motions are well aligned with this planar structure. So at least for two, it looks like they also seem to co-rotate within this planar structure, which can indicate that indeed we have the similar case as around the Milky Way. So why am I trying to convince you that we have some kind of co-rotation going on? And this is if we go back to the simulations and look into how a galaxy halo, how such a galaxy group should look like. I can't show this now with video, but you have to trust me, is that on the one side, we would expect all these points here, those are the dwarf galaxies, so it looks like they are more like spherically distributed, so we don't see a planar structure here, a thin planar structure. We don't see that. And if we look into the motions of these dwarf galaxies or these subhalos here, they are quite chaotic. They move randomly. They don't show this high coherence as we actually observe in the local group. So while we observe order and some kind of co-rotation, what we would expect in our dark matter cosmology is that the dwarf galaxies would be close to spherically distributed and their motion should be random. This is the so-called plane of satellite problem. We can, of course, quantify this. We can take all the analogs in the Millennium 2 simulations, measure their thickness, and measure their correlated motion, as I explained before, the scatter of the angles. And we take all the analogs. Those are the blue crosses here, and put the Milky Way, the observation of the Milky Way. We see that it's roughly a 0.1% outlier. So there are some analogs there, but that's mostly chance projection, because eventually you will find something which will look like a plane of satellite just by randomly drawing from a random distribution. What I find highly interesting here is there's another simulation, this Elvis simulation, these red crosses here, and those are more higher resolution simulations which came later. So with better simulations, the problem actually got worse. So it shifted towards thicker and less correlated analogs. So the tension between observations and simulations became larger. And I find this is highly interesting because normally once we improve a model, we can solve the problems, as for example with the missing satellite. But here it looks like if we go to better and better simulations, the tension actually worsens. So I'm an observer, I'm not a simulator. So I raised the question, okay, is the local group perhaps this outlier here? So do we see that just by chance? The universe was just randomly selected that our Milky Way has this structure, but other galaxies behave as expected. So in other words, is the local group unique? And that was actually the topic of my PhD thesis and is still dominating my current research. And to answer this question, what we need to do is to go outside of the local group. We need to find new dwarf galaxies around other galaxy groups, get their distances, so their 3D positions, get their velocities. And if we have this information, we can compare it to cosmological simulations to see if the local group is unique or not. So a no-brainer to go to is just the next galaxy group beside our own galaxy group. So that's our local neighbor. It's separated from us, so it's the Centaurus A group, but it's just the next group at something like 4 megaparsec, so very close. And this consists as the local group of 2 biggish galaxies. So Centaurus A here, and which is a beautiful spiral. It's getting late. A beautiful elliptical galaxy here, and M83, this spiral galaxy up here. So before our survey, roughly 50 known dwarf galaxies were already known. We observed roughly 500 square degrees. That's a huge portion in the sky to search really for this whole field for new dwarf galaxies. I don't go into the detail on the dwarf galaxy detection. So those red dots are the new dwarf galaxies we found. And we followed them up with the VLT to really get the distances. And for that, we really need extremely good seeing, because what we want to use to get the distances is the red giant branch stars. So we need to see the tip of the red giant branch, which is a distance indicator. We're from ground-based imaging, so you need a 10 or 8 meter class telescope with excellent seeing. So here's a snapshot of several of our VLT follow-up of the dwarf galaxies. And you see that, okay, several of them indeed we could resolve into their red giant branch stars, like these dwarf galaxies here. But there are some kind of odd things. For example, here, there's nothing. So that was really just some ghost in the images. Or here we have some dwarfish looking galaxies, but completely unresolved. So those are in the background. But I really like this galaxy up here. If we zoom in, that's a really old galaxy that's known, I think it was discovered by Stephanie Cote, which is in the audience. I don't know, I don't see it, but yeah, is at your place, I think, yeah. So this dwarf galaxy was discovered here, I think. And it's been in the literature. It was in my catalog as well for almost 30 years now. Well, 20 years, not 30. And now with follow-up observations, what you actually see is that this thing is a spiral, an extremely low surface spiral galaxy in the background. So you see this spiral arm here and here. And now if you go back into this image here, you can start to imagine that, okay, perhaps you could see it. Perhaps now that you are smarter, then you could. It's extremely difficult, but this made me think about, can we somehow from these images tell if it's a spiral or not? And just from the discovery images, can we somehow use the information of the pixels we see to classify those as dwarf ellipticals or as spiral galaxies? And that's actually a fun story about COVID, because my partner, she's doing a PhD in machine learning. And of course, during now the lockdown, we had a lot of time. We shared office together. She does medical image analysis, but we were a lot discussing about how one could approach dwarf galaxy classification with neural networks. And eventually, from just discussing this during the breaks and during walks, it became a project we worked together on. So we were thinking about, okay, can we somehow train a neural network to select just from images, just from unresolved images, if it's a dwarf galaxy or if it's a spiral galaxy. So to do that, to train any machine learning model, you need a huge sample of training data. And I did that, that's actually now accepted, but I took a galaxy catalog for low surface brightness galaxies from the Dark Energy Survey, which was something like 6,000 low surface brightness galaxies. And I went through them by eye and basically said, spiral galaxy, dwarf elliptical, dwarf irregular, spiral, spiral, spiral. Did that a lot of time to really have a ground truth on these galaxies. So then we trained a convolutional neural network. So we fed these classes in and tried and taught the machine how these things look like, and then tested this on a different sample we set aside. So we are not so used in astronomy, I think, to look at these confusion diagrams. So let me quickly guide through them. That's the result, or that's the performance of this machine, this machinery of this neural network after the learning. So here is the actual class. So what I set by eye, so this is a spiral, this is a dwarf elliptical, or this is a dwarf irregular. And this is what the neural network is predicting. On the diagonal, it predicts it correctly. And if it's off diagonal, there's some kind of confusion. What we see is that the neural network, it can classify 85% of the spirals correctly, even 94% of the dwarf ellipticals it can classify correctly. So there's just a minor confusion with the spirals. But for the dwarf irregular, it's super difficult. And I can show you exactly why it's super difficult. So yeah, for those, it works really well. These things here, is this a dwarf elliptical? Is this a dwarf irregular? It's super difficult to tell. And I'm sure that if I talk with 3 dwarf galaxy experts, I will get 3 different opinions on what this is. So I'm not surprised that this doesn't work out yet. Also, if you look here, those are the absolute numbers of cases we had. So we had a lot of spirals, we had a lot of dwarf ellipticals, but we only have a few dwarf irregulars. So that's also biasing. So we have not enough training examples here. So that was just an intermezzo of just the recent work we did on trying to figure out if something is a dwarf elliptical or a spiral galaxy before we do follow-up observation. And I think it looks quite nice. So I think that's something we can use in the future. But let's go back into this plane of satellite problem. While we were looking for the dwarf galaxies, another group actually scooped us on the question of if there is a plane of satellites. And that was Brent Tully and collaborators. They took the just then known dwarf galaxies there, and they suggested, hey, there are actually 2 planes of satellite there. So indicated here in red and in blue. So here in the middle, you see Sen A. Here's M83, and you can imagine here all these red dots, those are these dwarf galaxies in this one plane, and those are in the blue are the dwarf galaxies in the other plane. And we studied this And when we looked at that, what we saw is here this dashed line is actually our line of sight towards it. So we see this like edge on, we see really into this planar structure. So these lines here, those are the distance uncertainties. So once you see that, okay, this is not dominated by the distance uncertainty, so you really see that there's some kind of flattening. We, of course, had now new data, and it really doesn't look like there are actually two planes of satellite. It looks like there is some kind of pancake, some kind of planar structure, because we are missing dwarf galaxies here and we are missing dwarf galaxies up there. But really, you could also imagine, okay, there's some kind of boundary still here, but it really looks like it's some kind of flattened structure. But there is some kind of flattened structure. And if we see this edge on, as I said, if we look into this, and this is now the same as we have in the Milky Way and Andromeda, so we can assume there's some kind of co-rotation, we would expect a signal that on one side, the galaxies are moving towards us, so they are blue shifted, and on the other side, they are moving away from us, so they are red shifted. And this time, instead of just trying to acquire new data, we were a little bit smarter and we're thinking, okay, hey, let's look at the archive first before we acquire some new data. And actually, for velocities, there were already data out there in the literature for the last 20 years. And we just plotted it. And what we saw is, okay, exactly on the one side, they are blue shifted. On the other side, they are red shifted. So for 14 out of 16 of the dwarf galaxies, so the plane of satellite is in this north-south direction, which you can see here really. And here's the splitting line, and it's really looking like there's exactly as in our thought experiment, blue shifted and red shifted. So there seems to be some kind of co-rotation going on in this galaxy group as well. So we can, of course, quantify this a little bit better with position velocity diagrams. If this is a system, a pressure supported system, as we would expect from the simulations, what we would expect is that all 4 quadrants would be occupied by the data points. If it's a perfectly rotational supported system, then only 2 out of the 4 quadrants will be populated. And if we look this now for all these 3 systems, so here for the Milky Way, here for the Andromeda galaxy, and here from the Sen-A galaxy, so it always looks like 2 out of 4 quadrants are mostly populated. So this is, this is highly significant. And the frequency of finding this in the simulation is given for the Milky Way of roughly 1 to 1,000, for Andromeda 1 to 1,000, also for, if we assume that's the same for Centaurus A. If we now say, okay, that's 3 times finding this, what's the odds of that? That would be this number. However, I strongly disagree with just multiplying. You see some people doing this, just multiplying this. I strongly disagree, because we only can multiply these random variables if they are independent, and that's, we don't know. We don't know if they formed in the similar environment. Actually, we know that they are close to each other, so there's some dependency, so we cannot simply say that it's 1 to 1 billion. However, it tells us that there is something odd. So as I said before, we also looked into the simulations for Sen-A, and we see basically the same picture, that only a few of the analog, this times in Illustris. So that's a cosmological simulation which includes baryons. So there you have the stellar feedback and all these things. The Millennium simulation, that was dark matter only. Now we have the baryons in the galaxies, and the picture basically looks the same. So we have this 0.5% that we find this correlated motion. But but you may ask that, okay, I said something about 50 dwarf galaxies there. We just observed, or we just have data for 16. So that could be a chance alignment, so that it could be just a fluke from low number statistics. So we followed up now to see if this picture persists or not with Muse. So get the spectra to get the velocities. Here is why Muse, these IFU measurements are really like perfect, because the dwarf galaxies, they are low surface brightness. So you cannot just put a slit on them. That's extremely difficult to get any signal for these gas poor systems. But if you just have all the spectra at given pixels at every spaxel and put them together, you can get a nice spectra. And the dwarf galaxies, they perfectly fit into the field of view of Muse. So you really can exploit the capacities of Muse. So we used to observe these dwarf galaxies, and you really see that we can get some really beautiful spectra out. So nice H beta lines here and H alpha and the calcium triplet. And there's Muse is fantastic because you also make some kind of unexpected discoveries, because you can make images, you can use it as a narrow filter. You can produce narrow filter images. And for example, for this dwarf galaxy here, where the continuum looks like this, if you make a cut at H alpha, you see that there's this kind of strange feature in there. This ring, this is off-centered. If you look into the continuum, that's not centered on the galaxy, but really off-centered, and it has a diameter of something like 50 kpc. So we don't actually know what it is. It could be a supernova remnant, but for a supernova remnant, for a bubble of so that's emission. So somehow there needs to be some gas to be ionized, and it's a gas poor dwarf galaxy. So it's a really strange case which we don't know, but those are cool things you can look at when you have IFU data, which at the time we proposed these observations, we didn't think about looking at this. That was really just chance finding. Also, you can find globular clusters, for example, here. Those are globular clusters, and here's even a planetary nebula, which you just get for free if you have these observations. But here for the plane of satellite, we are mainly interested in the velocities. So here's the picture which we have now by adding new data points. We still have this co-rotation signal, so most of the dwarf galaxies towards the north are blue shifted and towards the south are red shifted. It's now 21 out of 28. So it's not a perfect signal, but it still looks like it is quite a significant signal for co-rotation. And before I continue, how much time do I still have? 5 minutes or?
Yeah, about 5 minutes.
Okay, that's good. So I made the point before that we used Illustris. And in Illustris, you actually have two runs. You have the dark matter only run and the dark matter plus baryon runs. Sometimes people say, okay, by adding the baryons, you will completely change the picture, so you cannot tell anything. So here we can directly compare the two things, so the dark matter only run and the dark matter plus baryons run. And if you look at the left picture, the dark matter only and the dark matter plus baryons, that's basically the same picture. So in my opinion, the plane of satellite problem is not affected if we include baryons or not. And it makes sense, because if you think about what is happening within a galaxy, so for example, supernovas, for the gravitational potential, so the distribution of these galaxies around their dominant gravitational component. What is happening in here doesn't really matter. It will not affect the motion. It will not affect the orbit. So it makes sense that the pictures are the same. So the physics on what happens on Earth if there's a volcano eruption will not change the orbit of the Earth around the sun that significantly. So what are the ideas to explain this plane of satellite problem? There are three scenarios which are passed around in the literature. Those are that these are formed through filamentary accretion, that these are formed through group infall or through tidal dwarf galaxies. So let me briefly summarize. This filamentary accretion, we have seen it before, is actually the main driver of galaxy formation and the main driver of what we see in the simulation. So all the halos fall in and they start to orbit. And one of the main problems is that the filaments are too thick. So if you have a huge filament, then you would need somehow to get the dwarf galaxies get compressed into this planar structure. Also the motion, because they will fall through all these different angles and different directions, so the motion should also be quite random. So we saw that this doesn't really add up. Another interesting thing to think about is that perhaps all the dwarf galaxies fell in at the same time. So we have this group of dwarf galaxies falling into this halo and start to orbit. That, of course, then would explain why all the dwarf galaxies have the same motion. It's actually a good idea, but it's observationally not supported because around the Milky Way, we have 10 plus dwarf galaxies, around the Andromeda, also around the Cenae, and such groups of dwarf galaxies with only, in real observations, contain only 3 to 4 dwarf galaxies. So they have not enough dwarf galaxies to bring all these dwarf galaxies in and explain these satellite systems. The third idea is that the dwarf galaxies formed through tidal interaction. So these planes of satellites came through tidal interaction, and it's quite an intriguing idea. If you have two spiral galaxies interacting, you form these tidal bridges. These tidal bridges, they form in the plane of interaction. So those bridges will then collapse and form tidal dwarf galaxies. We see this in observations, and they will inherit their angular momentum and then will start to orbit within this plane of tidal interaction. So you immediately get planes of satellites out of three just from the formation of tidal dwarf galaxies. However, there's a problem. Tidal dwarf galaxies are dark matter free. These tidal bridges, they don't care, as the dark matter halo doesn't care about these tidal interactions, and you will not rip out any dark matter subhalos out of this. So these will be completely dark matter free. But as I showed you the plot before, dwarf galaxies are the most dark matter dominated objects in the universe. So there's basically a conundrum there. One way to solve this would say, okay, our model of gravity is wrong, and something like MOND could then be the solution. But yeah, that would basically change the whole of our understanding of gravity and cosmology. And if that's really what we want to do to solve the plane of satellite problem, I don't want to say that. So there's one other solution. I hinted towards that before, that we are all very close towards each other, and we are at the border of this local void. And actually, if we look into this compression of this local void, so the structure is forming, is getting compressed, it also gets stretched by the Virgo cluster. And if we look into this direction of compression, angular poles of the Andromeda and Centauri, they are aligned with that. So it looks like this plane of satellite is basically pointing or is perpendicular to this local void. So that could mean that the local void and the Virgo cluster could have formed these structures. For the Milky Way, this is off-centered. So that's not a good explanation for the Milky Way, but it could be that these things are a mixed bag of objects. I'm skipping this part and I want just to go to my conclusions. And I think I'm over the time, so I'll leave it at that. And thank you very much for your attention.
Excellent. I'll clap for everybody, as we tend to do these days. Thank you so much for that excellent summary, Oliver. I think we can all agree those are some very intriguing results. So we'll open the floor to questions right now. Just use the raise hand feature if you don't mind. And while everyone else thinks, I wanted to ask, early in your talk, you were listing the various challenges to Lambda CDM that the planes of satellites seem to be adding to. Has there been any effort to kind of marry any of them? Like, it seems like the list is getting long enough that perhaps one or two or maybe three of these challenges might be interrelated. Can you comment on that?
Yes, so the trinity of all the problems, the CUS core missing, satellite and too big to fail problem, they are very much connected. So I'm not the right person to talk about how you can exactly solve it, but there are some claims that you can solve them by correctly including the baryons, for example, with having supernova feedback. I think you can transform a cusp into a core, so you can reshuffle the dark matter halo. And with supernova feedback, you can also destroy halos. So you also solve the missing satellite problem. But then the too big to fail problem, for example, because that's the most massive galaxy, this will not be much changed by this. So I think there is not a solution which can solve all of the three problems at the same time. There's always a caveat. So but there are multiple solutions for the multiple problems.
Is there a way that the planes of satellites can jive with kind of these big three, or is it kind of a problem on its own?
I think it's a problem on its own because the other three problems, they are basically a problem of what is happening within the dwarf galaxies, while the plane of satellite problem is a problem on how do we form halos, how do we form bigger halos, and how do we distribute the galaxies. So that's, I think, a really a different question.
Mm-hmm. Well, fair enough. Joel, you raise your hand. Go ahead.
Thanks, Matt. Very nice talk, Oliver. It's very cool to see this data that you're putting together, and yeah, I look forward to seeing what comes in the future. Speaking of that, actually, maybe I could get you to play the part of Nostradamus a little bit. I'm curious, this is just a minor curiosity really, but when might we expect to kind of fill in the gaps on the 3D motions of the satellites around M31? You mentioned that we now just have recently have gotten proper motions for 2 satellites in the plane. When do you think we might be getting more data?
So that's for that we need a long baseline. Unfortunately, Andromeda dwarf galaxies have been observed the last 20 years, and I think there is now an approved program by Tony Sun, if I remember correctly. for other dwarf galaxies around M31. So I think really in this cycle. So I guess soonish. I guess very soonish, and yeah, it's coming and it's possible. However, for CNA, even though the HSD programs are also, the last ones are 15 years old, with HSD accuracy, you will not get any proper motions. So it's really a shame. So you would need a baseline of something like 50 years or more. And yeah, not possible, sadly.
That might be more the ELT kind of problem,
Yes.
right? Yeah, or TMT. Yeah, great, thanks.
Okay, we still have a few minutes, so there's plenty of time for another question or two, if anyone can think of any. Oh, Julio, nice timing.
Yes, thanks, thanks, Matt, and thanks, Oliver, for the talk. That was wonderful. Now, I think if I understand correctly, the evidence in CNA is more of a gradient in velocity rather than a particularly planar structure. That doesn't seem particularly planar to me, although one can quantify these things, I guess. But is it surprising perhaps that there is a gradient, given that CNA is widely interpreted to be as the remnant of a recent merger? I mean, wouldn't you expect a remnant of recent merger to have things different on one side than the other?
Yes, so actually a student of Marcel Pawlowski was looking into, I think it was Illustris, to check for the analogs we have here, which resemble NA, to see if, for example, there is some kind of evidence for that they experienced a major merger. And it looks like it's not necessarily. And then he also looked into major mergers, really major mergers, and how a major merger will affect the phase space distribution. And what it does, contrary to what was previously shown by Rory Smith, it actually destroys any kind of coherence we could see. So I think the major merger, while it makes sense that perhaps during, because I mean, it still can be that we are very close past this major merger, that it has an effect. I don't think it is the solution. But yeah, it's something which is looked into it, and the paper will come soonish, I think. So yeah, this topic has been addressed, but not by me. So I haven't done that. So I don't know the details.
I understand. I guess I was just wondering, imagine you had seen the antenna galaxy, right? You have an antenna galaxy, something in the middle, and two obvious, things coming one side or the other. And imagine that, the dwarfs were tracing the structure. You see that, one side of the galaxy has a very different mean velocity than the other side of the galaxy. So it would seem to me that it's relatively easy to come up with gradients just out of equilibrium features in the case of major mergers. But
yes.
So I was just wondering whether one can come up with an actual model for CNA rather than a statistical arguments, which hide lots of things in statistics. So.
Yes, yeah. So I agree that could be a really interesting thing to look into. I wonder now about when we have proper motions, as we have in the Milky Way, then then we would expect basically a different signal, because we would expect some bulk motion one side with the proper motions and on the other side. So we wouldn't expect a co-rotation around the Milky Way if such a major merger would have formed all of the three planes of satellites. But I agree that for CNA that could be an interesting solution. Yeah.
Okay. Well, thank you. Although the Milky Way, of course, we have the recent accretion of the LNC. So in some sense, it is an ongoing merger. Right? And we know that many of the satellites that we identify with the plane in the Milky Way
Yeah,
are
but
clearly associated with the LMC.
There's a timing argument because you have some plane of satellite members on the opposing side of the LMC. So if you have the Milky Way here, LMC here, you have dwarf galaxies orbiting here. And if the LMC is on its first passage, as I think what we agree upon at the moment, it doesn't make much sense how it could have brought the dwarf galaxies up here, right? Or would that then be?
I wasn't thinking that. I wasn't thinking that the whole plane was caused by the LMC. I was just thinking that perhaps, you know, we know the distribution of satellites are anisotropic. Imagine the anisotropy is due to, you know, the presence of an initial, you know, sheet of matter or filament, and the LMC is part of it. So you have an existing anisotropy that then gets enhanced by the recent addition of the LMC on a similar orbit, because everything is part of kind of the same, you know, larger scale structure. So, but you know, unfortunately, as you well know, once you have an individual, once you look at it very carefully, you always find things are very odd. So, how to generalize them, what is of general applicability, and what is it's really hard. But you know, clearly, the oddballs and oddities they may or may not be meaningful, but it's exactly that you're looking at this.
Exactly. Also here, I mean, if we do this comparison to simulations, we are basically just randomly sampling all the different halos, and if this is really the correct way to do this, that's a statistical way to do it. But for example, what could be really interesting as well is to have constraint simulations like Hestia, Clues, something like that, and look at exactly things resembling the Milky Way, Andromeda, Centauri, Virgo, and all these things, and then see perhaps this shows us that we form these things naturally, just by how matter is distributed and how things fall in. So it could be.
Yeah, no, there has been a lot of work on that recently, on, you know, reproducing local group environments together with another larger scale flow. And unfortunately, I think, you know, there's so much stochasticity on the small scale distribution of satellites. It's going to be very, very hard to map them to, you know, in other words, you can go to exactly the same local group analogs, but they have very, very different small scale structure, environments, and acoustic histories. And so it doesn't seem to be enough to constrain that. There's no surprise in it. There's very little information really about the initial conditions on large scales on the very, very small scale. So I'm a bit not completely convinced that we will learn too much more from that. In the case of statistics, you know, I think, you know, one needs to be always aware of the look elsewhere effect. You find an object, you look at it to death, and you find something is odd, and then how do you account for the fact that you looked at it until you find something that is odd? Right? It's a bit, it's really hard to take into account, and that's why the particle physicists ask for 5 signals that are not basic.
And exactly that, that's why I also said this this multiplication of the probability, that is something which we are not allowed to do exactly with, or else we completely screw with statistics and say everything is wrong by doing.
Wonderful, thanks.
Yeah, well, I think it's fair to say that the results are at least very intriguing, and I think we all appreciate when science comes up with more questions than answers. So, in any case, we're a little bit past the top of the hour, so I think we'll draw this to a close. So let's thank Oliver again for his time and for presenting his really excellent results. So, thank you very much, Oliver.
Thanks for your attention and thanks for inviting me.
It was our pleasure.
Thanks,
hopefully soon again, in person again.
I hope so. We'll cross our fingers, yeah. But
thanks for indulging us at the late hour in Europe.
Absolutely, yeah. So go get some sleep.
Yes.
So much.
Honestly,
Bye.
yeah. So,
All right.
yeah, bye.
Ciao.